In this module, I will discuss the global atmospheric engine. Understand that the atmosphere constantly receives energy from the sun, and this is the major driver for global air transport. The energy from the sun causes gases to expand and compress. Due to the difference of heat inputs at the equator versus the poles, the rotation of the Earth, and the different heat conductivities of the ocean and land, atmospheric transport and weather is produced. Consider this image of solar incidence on the global surface. The angle of incidence changes at the poles versus the equator, and this creates the different energy input for these two regions. Because of this, we all know that the equator is hotter than the poles. This heat difference, as well as the pressure differential, and the fact that water versus land will reflect that energy back in different ways, creates what's considered global air transport conditions. Before I show you some of these major jet streams, we also need to consider that the Earth is rotating. If there was no rotation, wind that is generated when air moves naturally from high pressure to low pressure would go in a straight line. So consider here a simple high pressure system in the center, and air will move from high pressure outward to low pressure. And that movement of air will generate what we call wind. Now, if we consider this at height in the atmosphere, so here we have height in the atmosphere, the high pressure system in this case is at height, and this is also going to correspond to colder temperatures, and as we get closer to the Earth's surface, warmer temperatures. So as we consider this situation, the high pressure air will move toward the low pressure air in the arrows that are indicated. Now at the colder temperatures, the gas volume is small, and as it moves to the warmer temperature, gas expands in volume. So this is related to the ideal gas law, PV equals nRT. At the colder temperature, if we have a set mass of water vapor present, as the gas expands as it moves down, the relative humidity drops. The same amount of water may be present, but because that gas has expanded in volume, the percent humidity in a given volume of air is lower. Because the relative humidity drops, in this situation, there is no rain present. And so in this situation, this is representative of ideal weather conditions. No rain, clear skies. Now, if we consider this on the global surface, we'll see that the high pressure systems on the globe are at the poles, and the low pressure system is at the equator. And this creates a global air pattern of air that moves from the high pressure to the low pressure in both hemispheres. And this is how we've divided the Earth into latitudes based on tropical, subtropical, subpolar, and polar regions. Again, we need to consider, though, that the Earth is in rotational movement. So Newton's first law of motion and the Coriolis effect state that an object in motion tends to remain in motion unless acted upon by an external force, and an object moving in a straight line will continue moving in a straight line unless acted on by an external force. So in this case, we have air, or wind, that is going to be moving in a straight line from the pole to the equator. But because the Earth is rotating, the atmosphere experiences a centrifugal force, and the overall effect of this is called the Coriolis effect. The centrifugal force by the Earth's motion creates an angular thrust to air movement between high and low pressure systems. And so instead of that air actually moving in a straight line out, as the air moves, the rotational or centrifugal force causes the air to move at an angle. And so here we see the simple system in a two-dimensional framework, and here we see it in a three-dimensional framework, where the high pressure and the low pressure movement now goes at an angle. This situation is called the anticyclone. The definition of an anticyclone is written here as the circulation created by high pressure areas where air will subside or move downward in the atmosphere. As air warms as it subsides, it has a corresponding drop of relative humidity, and this is associated with clear, sunny skies and mild weather. Now, the opposite situation for an anticyclone is the cyclone. When a cyclone occurs, circulation is created by atmospheric low-pressure zones that create areas of rising air. Air cools as it rises, and water condenses. This creates clouds, rain, and hail. The most intense cyclones are tornadoes and hurricanes. So cyclones are associated with foul weather. We can draw a picture of an anticyclone similar to what was shown before. So in this situation, you have atmospheric low-pressure zones. As you move down near the Earth's surface, you get toward a high-pressure zone. Near the Earth's surface, it's warm, and in the atmosphere, it's cold. As that air rises, the humidity that was present in a warm temperature was also in a large volume. And as that air rises and it cools, the volume shrinks. And so compaction, or compact volume, creates a situation where the humidity drops out and rain occurs. Depending on how strong the difference here is between the high pressure and low pressure system in the atmosphere, the strength of this cyclone will change. So if we put this all together and look at what happens at the global scale again, the Coriolis effect creates movement in what are called cells. And so the jet streams that you may have heard of if you fly an airplane are that each hemisphere is divided into 3 different cells where this movement from high pressure to low pressure occurs in each cell. And this creates what are called the jet streams or the westerlies. This is a picture in 3 dimensions that show these cells and the air movement from high to low pressure, and the Coriolis effect that shows how this creates some rotational movement. And the picture from space is really dramatic of these. So this is a satellite view of the atmospheric circulation at the South Pole. And you can clearly see this rotational movement within each of the cells near the pole. So in summary, why this is important for environmental engineers to appreciate and understand is that if you have an air pollution plume that makes its way into the atmosphere, it can be carried quite a distance on one of these jet streams. Air pollution travels globally. This has been recently appreciated in the United States. The nuclear accident that happened in Japan in 2011. Radiation made its way to the west coast of California within several weeks. And so we must think globally when we're considering air pollution and air pollution problems.